Well, we only went like a little bit hallucinogen with the AI at the end of that day, but it's kind of fun. And it's certainly more of a mimicker, in the same way children mimic, I guess. But it's, it was quite interesting to be able to look at it and interact with it, and then interact with human beings who understand a little bit more than me. But even then, I disagreed with them about some things. Okay. And so, what do I want to do here? All right, back to the lovely, lovely. Long road. Know me long ago. Before the storm, I know. Boy, if I did. Right. 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 Holy cow. Oh.
redial it at any time, or you may select one of the following options. For support with new or existing products, press 1. If you are interested in purchasing one of our products or services, press 2. For recruiting, press 4. For human resources, press 6. For shipping and receiving, press 8. To repeat options, press 9. For all other information.
Well, I called them and they said, the one person on the phone I talked to after talking about purchasing their services said, "Nah, you're good as long as you send them to our website and say that we own it. We're good. It's academic, so let's do it." Baby, I'm not a rose, I'm a wildflower. Rest her soul. Yes! Welcome, welcome, Easy. Chasing thunder. On the syllabus, it says that tests are no internet, but on the test page, it says internet is allowed. Yep, it's 100% allowed. Let me change that. Or, well, I gotta add that to the list of things I need to update on my syllabus. That is a really good reminder. Let me add that to my checklist. Where would I want to put it? Where would it be important? I need to have the midterm vote. I do need to respond to Canvas, but probably before then. So let's add it here. Update G syllabus. Internet is 100% allowed, but what I need to be more clear about is you can use the internet, but right now I'm still struggling with that. There is definitely a part of me that wants eventually to come to terms with the fact that in the real world, we all choose to be experts in different fields. And so sometimes we do go to other people and say, I just want an answer because your answer will help me in the expert field I'm going into. But Emory, in my contract, has asked me to make you that expert. And so I want you to use the internet because an expert would use the internet. But I don't want you to use it where you're an expert asking another expert to answer a question for you. And so that clarity is hard to define and possibly even harder to control. But you can use the internet. But I'm still not sure how to do it well. I think like if your stuff isn't like leaked, it shouldn't be on Coursera or anything like that. Yeah, but it's also like, if you go to a large language model, a real simple example is like when just the other day, last night as I was going to bed, I was filling out a form for an application I'm curious about, and they were asking questions on it. Like, if Sally has $10 and gets $2 every day, and Joe has $20 and gets, I don't know, $1 every day, after how many days do they have the same amount of money? And certainly it's just math, it's just functions. But I was like, why do I need to do this? I know the math here. I'll just go to ChatGPT, or I'll go to Wolfram Alpha, and I'll put in the right function and get the answer. And so if you guys are using, the large language model, for example, my whole question is, how can I make sure Emory knows students didn't just use a large language model to answer my questions. They used a large language model to help them reason through my question and produce an answer that both came from them and a tool they can use. So I don't know. Okay, so I don't know, but let me before before my ADHD falls apart, let's make a Google Doc a second, and we'll call it syllabus updates. I gotta remind myself I was going to update a few things. Rec letter wording, test and tool / internet use versus Emory needs me to make an expert, or maybe I should say semi-expert in chemistry, not an expert who asks another expert for the answer. And let's see other things. Good. Privacy be damned. I agree sometimes. There's this thought of like privacy is important and interesting to me. Privacy is very interesting to me. There's a certain use for it because it gets rid of biases. And I don't like implicit biases. It's like once I know who you are, suddenly things change. I'm no longer treating you like anybody. I'm treating you as the person I know you are, which is crazy. Yeah, it is whatever. And that's the thing. It's like it is okay for us to know each other and to start like realizing we have biases, and then we can work against them. So hiding from the fact that we have biases is kind of helpful, but at some point it's kind of interesting. But anyways, I'm also working through today's material. Can you explain what an E1 reaction is and how that relates to alkenes and easy stereoisomers. Yeah, absolutely. So let's even say E1 reaction, because rather than spending too much time. And you stream on Twitch. What is your Twitch? I'd love to. That's the thing. It's like this community. I knew students were out there. I knew you guys were out there. I just couldn't find you guys. Cool. Thank you. Let me put this in my student notes a second. Oh, you do work with waves? No, no. Okay. Well, let's finish one thing at a time, and then we'll get back to these lovely questions. Because this is legitimately what makes me enjoy teaching more than anything. Is that every day in my physical office when students came and talked to me, that was the best part of my day. Certainly, this is also the best part of my day. Writing this quiz is really fun, but okay, let's get to Canvas a second. Look in the announcements, and I gotta check some of my email because I emailed with students about what I would do too. So let's make sure all that's good and do one thing at a time because our brain wants to just jump. But we have to find ways to start getting better at that. So, okay, here we go. Boom, 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 boom. Go to my announcements a second. Syllabus is misleading. Yes, it is. Okay, it's misleading about when exams are chosen. That was the other thing that needs to be in there. Okay, blah, 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 blah. Exams are on the date shown and will be so rec letter wording is one thing. Test when is another thing that needs to be updated. And then the last one, what Cass is asking, tests how. And then kind of. Okay, that's done, so we can come back to that later, and then we're going to think. What was the other thing we were going to do? Student note. I want to add that I know something now about UCAS, which again I think will help me write a better recommendation letter. I hope. And I already have some nice notes on UCAS. I've really appreciated your commitment to class and commitment to contacting me. So, okay. All right, I got that figured out. Okay, now let's go back to, let's see what you said. I think everything goes right. Goes right tonight. I'm going to be streaming at like 11 p.m. trying to get to the fourth movement. Okay, cool. And I'm going to, just in another window really quick, pull it up. Twitch.tv/easyost. And I want to immediately subscribe. Okay, or I guess it's called following here. So freaking cool! Gosh, I love this so much. And I'm going to unsubscribe from this one, because that one's not interesting to me. Alright, we've got 2 subscriptions, or 2 follows. Okay, and I think if people do use AI write for the test, have them submit the chat log so it looks like you're talking and reasoning with a tool instead of pasting. I 100% agree. And it's not that hard to screen record. And I'm looking into with Emory, I need to check my Emory email about this Proctor service. And I'm not doing it to punish students. I'm doing it out of pure curiosity. And maybe it's a little bit of an unfair experiment to run, but I'm looking into it and going to have to decide, how will this help me? Does it just like watch you and tell me when you like make a weird movement? I don't know. But anyways, okay, back to your question. So So just to get it on file, AI is allowed on the test if you're reasoning with it and not just pasting the questions in. I really do want to say, and am going to have to also, let me just first start by saying, I think my colleagues would warn me, would convince me, would beg of me not to let students use it. But I have been so frustrated as a student that I wasn't allowed to use a calculator, that I wasn't allowed to use a cell phone, that I wasn't allowed to use notes, that I wasn't allowed to use things I would use in the real world. So why would I continue that process? So I would say for now, let's put it on file that I am very interested and curious and want to find a way to have students use all the tools available to them to be an expert in a field and answer the question themselves, not be an expert who asks another expert for the answer. And that will be my on-file answer, recorded, come back to it as of May 23, 2025 at 9:48 a.m. That's where I'm at. But I always reserve the lawyer, speak of, I am going to likely have to change this in the future because my colleagues will challenge me, will argue with me, will point me to resources that I have not yet interacted with. They are experts in pedagogy, and I am not. I am working on being a better expert in that world, but I'm not an expert in pedagogy. So, but I am a pretty good expert in being a student and being a teacher. That's what I've been doing for 30 years of going around the sun. But anyways, I want to answer your question. So, or keep chatting with you about this and then get to your question. But okay. So let's pull up. I agree. So let's pull up this a second as well. So a mechanism for the E1 mechanism. Let's find a good one. And we want to add orbitals to this at some point as well. Let's see if we can even find an example with orbitals. And we might need to create it ourselves. Dead internet theory. No. Chasing thunder. So this is an E2. So E2, the reason E1 is that there is, oh man. I'm just thinking about something right now. Oh, cool. Okay. So let's pause a second and just go back to something that I want to make more clear to you and to my students at some point. We talked about the SN2. Let's pull up the class slides a second. Baby, I'm not a rose, I'm a wildflower. Out of all the empty. Okay. And we should take a timestamp because this would be a great video I could cut from this stream and then upload. So, recording, where's my recording time? Let's take a note. My stream highlights. Where's my stream highlights document? Always chasing thunder. Oops, not that one. I need to get back on Reddit. I got shadow banned from Reddit for good reason. Okay, so it's been a while since I've updated this one, but boom! All right, Cass came in And we have approximately, where's my recording timeline? 1:48. Okay, perfect. So 1:48:39, we started talking about this stuff. So back to here. So, okay, one thing I want to talk about that's, I think, very important before we walk into E1 and E2 is let's activate prior knowledge. Let's prior knowledge, whether it is or not, that's still up for debate. But in here, I said that there were two mechanisms you had to learn. You had to learn both SN1 and you had to learn SN2. And at first glance, you might be like, this is weird. SN1 is a two-step reaction, so why is there a 1? And SN2 is a one-step reaction, so why is the 2 there? Well, it's because to prove these things, the evidence says SN2 is bimolecularly limited. Its rate is limited because the slow step is bimolecular. And so the 2 is because there's two things in the rate law. SN1 has only one thing in the rate law. So if that's the case, there's some relation possibly between what you saw in SN1 in SN1 versus what you're now going to see in E1 when I explain E1 to you. So in the SN1 reaction, the reason it's unimolecular, the reason why no matter how much nucleophile I dump in, it doesn't matter. Why does it need protic, and how does that stabilize the carbocation? Yep, exactly. So this is solvent effects. And it's about going, you're still thinking about orbitals, certainly. Where's my, is it Chem Libre would probably have a good example of it. Oh, here we go. So let's just pause for a second because this is all going to be great on the video. Because this was the thing in lecture where it's like, dang, I wish I could talk for hours and hours and hours about this stuff, but I can't. And I need to make, yes, I am literally taking a class that passed the Emory grade. Like, thank you, Dr. Weinshank, for, technically I can just take his stuff, copy, paste it, and walk away from it. But that helps to give the students more resources. Heck, you guys should be looking up this guy. This guy is another genius that we have underneath Emory that I have not even shared with us, that I need to share with students. Like, this guy is a genius in the best way possible, and a kind genius. Like, if Cass, for whatever reason, I don't explain things in a way that makes sense to you, there are other people who can explain things to you that are part of the Emory ecosystem, and this is one of them. And so he might have something, I'm not sure if he has something on solvent effects. But if he did, it would be an awesome video. So anyways, let's go back here. So, okay, blah, 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 blah. We don't care about nucleophile. Oh, this is not particularly good. I want to have... It's about stabilizing the transition state, is the short answer to your question. Okay. Okay, here we go. Boom. This is your answer. So in the unimolecular SN1 reaction, the leaving group leaves and a carbocation is formed in the first step, which is also the rate determining step. So that's why it's 1, is because it's unimolecular. Now, the polar solvents, such as water and methanol, can form hydrogen bonding with the leaving group in the transition state of the first step, thereby lowering the energy of the transition state that leads to the carbocation and speeding up the rate determining step. As a result, polar product solvents facilitate SN1 reactions. It is very common that polar product solvents also serve as nucleophiles for the SN1 reaction. So SN1 reactions are usually solvized reactions, as we learned earlier. So this is the answer here. It's this picture here. And if I pull up paint for a second, just remind yourself that there is, the leaving group has to leave. So this is, what am I drawing? I'm saying that this is, I know this is inaccurate. I want to say time, but it's not. Yes. And so this is called the reaction coordinate. I sometimes think of it as time, but that's not really appropriate to think of it as time. It's better to think about a coordinate. As you pull things apart, as you move X and Y and Z, in our case, really just X and Y, I leave a lot of chemistry on a white piece of paper on something I can write on. And so this reaction coordinate is just in the X, Y directions. But anyways, we have this reaction coordinate. And so here is the... and so here we have, I'll make it very simple, and I'm taking this molecule here, and what should I use? What did they use? Okay, they don't do anything. That's great. I actually like that. That's a more interesting picture to draw then. So, see, you know what's so sick though is I do have one, and I found my Apple Pencil. Let me go get it before I lose it again. Oh, my back. But like the funny joke to me is that the joke is that doctors don't have good handwriting. Why do doctors not have good handwriting? Why do they not care about writing things well? Is it because they demand raw efficiency? Does it like, I don't have time to write. It's up here and I can type it maybe one day. And that's the better way for me to do it because I've played video games all my life. I can type stuff really well, but I can't transfer information visually very well. Anyway, so I do have it. I'm working on it. But okay. So back to this kind of thing. What we have to consider is first, we could say, let me make sure we can get these pictures kind of together. Or I could even snip it and pull it onto everything. Okay, I could actually do that, and that would be the way to do it. No. All right, snip again. Baby, I'm not a rose, I'm a wildflower. So consider this. Let's go to Google Slide Pictures, Desktop. Let's just do new folder, Student Talk. Windows Shift S, and then it's in your clipboard. What do you mean by that? Thank you for teaching me. I love to learn. That is my favorite thing. SN1 solvent. So if I take this thing here and I do Windows Shift S, no, thank you, Cass. And I go here, and I can't show history, that's fine. I don't want to, but I want to put it in here. And it does. Thank you. Okay, wait. Pause. Learning, for me, requires one of the most amazing inventions. Where did I put that invention, though? Did I put it in here? I might have. I did. Okay. Best invention ever. Right there. Oh. Windows Shift S, then you go to paste into Paint. Ahaha. He can learn? He can do it too? No. All right, add it to the many other Post-it notes. But, okay. So, this will make so my reaction looks less trash now. And we can do full screen back to here. Okay. So let's get rid of this, and let's try to even make it even cleaner. Kaboom. And let's go here, and let's just say, bring it down a little bit. Ooh, we're making a diagram. Too small. So let's define our axis. That might be inaccurate, but for now it's good enough. So, okay. we know that if we just throw into a computational computer that has a basis set and we say, take a look at this, I want you to tell me, computer, and we'll just define for sake of argument. We could make up x. We could say x is some new element, but for sake of discussion, let's say x is BR. Because it needs to be some good leading group, something kind of big and bulky. So we'll say x is BR. Okay, so this has some energy to it, but what I need to add to this is this energy is going to change. Why is this energy going to change? Because me and you are not talking about this. Well, actually, let's talk about this for a second. So I'm going to say, okay, first step of the SN1 reaction is it takes energy. So what's happening when I just drew that line? Well, what I'm doing is I am moving how far or how close things are. And so I'm taking this, and once I kind of am maybe here, when I'm here on the graph, what I've done is I've taken this bond and I've just moved it. I've moved it out. Snipping, you can do Windows Shift 5 and you can copy and paste that image. Does that open it automatically? It does. But I almost like that. It's built into Windows now, isn't it? But it goes to my clipboard, so I get it. So I use the snipping tool if I need to save the image. But if I'm just grabbing it and pasting it into a paint I'm already open, I use Windows Shift S. But if I need to quickly open up snipping tool, it's Windows Shift. Windows Shift 5 is the snip tool. Thank you, thank you. What happened? It says I'm unable to connect to chat. Certainly I'm still on the tube. All my data looks good. Alright, so let's just look at the chat here then instead. Alright, so let's just look at the chat here. Oop, there, it's gonna come through again. Okay. Also, that means it's most likely endothermic. What are you asking is endothermic? Because I think you're right. I think it is endothermic. I think it does end up at a higher energy state. I guess it depends on. Yeah, it is, right? If I'm taking two charges, I think it would be. I agree. I think it would be. Gosh, nice. Very nice. No, it goes into your screenshots folder too. I have a screenshot folder? What? See users, your username's picture screenshot. Where is it? Where is it? Maybe I need to add some functionality that I've turned off. So anyways, okay. So again, just so you realize, I'm now my chat here. How can I maybe refresh this? Get rid of this. Get rid of this. Go here, go here, go here, go here. View. I'll just work here. This is fine. Okay. So this halogen is moving away as I go across the x-axis on the graph. And so at some point, there is some amount of energy that we reach, some level of energy that we stay at, because my stuff is far enough away from each other, right, that now the computer is defining, and I need to make sure I grab this picture. And sorry for the poor snip. I'll do it better. Why not? Why not? So at some point, we separate these things. We pull this bond completely apart that we have. The computer calculates this is, we're making the assumption without calculating it, but I think we just know this to be true, that you pull these things apart, it's going to be higher in energy. Why? Because you've created charges. The carbon does not want to be electropositive. It wants to fill its octet. The halogen is actually kind of okay. It's filled its octet, so that's a stabilizing feature for it. And so I think, though, that it is, when we take both of them into consideration, it is a high energy. So this is where we now can understand solvent effect. And so if we ask ourselves, we make another graph. So let's get this over here where we can pull from it later. And to make this a little bit better, let's kind of consolidate our graph a little bit. Okay, great. So now take this, copy and paste it again. So this is, let's make a note. Notice how the only molecule I am asking the computer to generate energy for is the SN1 molecule that has the leaving group that just leaves sometimes and sometimes not. Right? If there's energy in the system, if things are bumping into each other, at sometimes this bromine does come off, and then sometimes it snaps back together. But that's happening. So this is no solvent, and that I need to make real clear. No solvent. Bold italics, make it big. And so you'll okay, fair. I'll just write it in here then. No solvent. I bet for a lot of students, and I wonder if you feel this way, Cass, it's like I remember what it's like to, because I do it a lot, working with my mom and watching her work with a computer is so cute to me because she wants to do it, she wants to learn, but she does not have the experience I have. And then there are students who watch me do what I'm doing here and they're like, oh man, he's so slow. But I'll get better if I keep doing it. Anyways, okay, so what I want us to consider now is what if, instead of showing the computer just this, what if we told the computer, okay, I'm going to give you now one extra molecule. I'm going to give you a polar solvent. And this is going to now make things really, 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 really complicated. Is there a one that's not charged? Well, I guess I can fix it myself. How do I center? I want to center on the thing that I'm looking at, but I'll worry about that later. So get rid of this. So now I go to the computer and I say, okay, computer, now consider the fact that there is two things here that we're considering. And so because I've added a new molecule in, water and this molecule at some distance, near or far from each other, has a new energy level. I remember teaching music theory drawing on PowerPoint. Nice. Oh, I can't wait for music theory to come into my life. I was having if you look at the Zoom recording that I posted for class, I talked to a student at the end of class who brought up music theory and how that's how they make the connection to constructive, deconstructive orbital theory is by thinking about music theory, dissidence, and some other big fancy word. But, okay. So again, I have to tell the computer how close or how far the water is away. So for now, I'm going to tell the computer that at this point, whatever this energy level is, I'm going to choose or say to it, water and molecule so far away that they do not interact yet. And maybe I'm being inaccurate here, so question everything I say here a little bit, and I'm questioning it myself, but I'm pretty sure this is accurate. So I'm putting these molecules as far away as possible, and so just fundamentally, this graph changes because this energy level, let's set it at a dummy value for us to just play with. Let's just set this at 1. Maybe it should be -1, but for now, for the sake of discussion, let's make it 1. So down here, this new value of water and a molecule has to be not 1. And so let's keep kind of going. Let's make more of this. And bring this with me. So it's not 1 anymore, so okay. Let me kind of clean this up just a little bit. So, okay, I have two molecules that I've told you at the start of the reaction coordinate diagram. These are far away from each other, and so I don't know what the energy is without a computer telling me, but I know it's not 1. So here it was 1, Here I'm going to say whatever value this is. I won't make the foolish mistake of trying to say what I know that it is, because I don't. No. Not 1. Great. And clean this up. Okay, so this is not 1. We have 2 molecules here. But what is interesting, what we want to measure, what we want to consider, is that there is some value here. And so for sake of argument, let's just say that this is, if you're okay with variables, let's just say this is x. And now when we come down here, this x has changed because I've added in 1 molecule. And this molecule can do one of 2 things. Either I can tell the computer, take the molecule, the 1 molecule I gave you, and use it, because now we're going to transition a little bit away from that picture, and now we're going to transition to this picture. And we'll say, here's one thing I can do. Once I rip the bromine or the X off of the carbon, and it's completely far away from the carbon, and now I let the water interact with it, that will stabilize it if it points the hydrogen at the halogen. And so this value now of, again, it took energy for me to break the bond. My favorite thing to do, and I've sacrificed these too often, right? Breaking bonds take energy. It takes energy to break bonds. So by the definition of me breaking that bond, that's why I go up on the graph. But this here in blue, so let's kind of talk up here. All I did was break a pencil here in this diagram. All I did was break a bond. Energy had to go up. To break a pencil, I had to put in energy. Endothermic. No, more definitions. Okay, down here though, oops, let's leave that. Down here though, what is this blue line? Not quite a full bond, but close. So energy must go down. So X here is not X. X, whatever value that we have here, the value of it must be less than X. And so to show that visually a second, I'm going to take this and say, it went down in energy. My new difference in energy is less than 1. And so what I want to consider for a second is we are stabilizing the transition state. We are helping this anion leave. But if I add in more water molecules as I solvate this reaction means add in more water molecules. Say to the computer, you have 100,000 water molecules that are sitting around these molecules. How does that change the energy levels of things that I want to do in the real world, in my actual chemical flask when I'm sitting at the bench? And what makes this tricky is we can't, because I can, let me just pause for a second and maybe that kind of lands a little bit, but let's show kind of what makes these solvents tricky sometimes. Not only can the water molecule stabilize the halogen, but what else can this water molecule do? And this is going to be, I'm not going to use this one. I need, where is it? Oh no, did I do the wrong one? Maybe I did. It doesn't matter. You can still look at the video. Okay. So I need from you this image. Oh, not quite that though. I need just this. Okay, I was right before. I need this. So right, this is like mind breaking in a good way. Not only can I have my free floating halogen that I ripped apart at a high energy, but notice on this molecule, where is it? Notice on water, there's two things that draw my eye. This is the theory I use to say this is what stabilizes this. But what could stabilize this? What part of this molecule could stabilize that? Yeah. Or being even more specific, you have to choose one part of it. I think you know the answer. I'm just making you be more clear. It's not the OH part. It's one part of the OH part. The H part stabilizes the X. But the other atom in the bond does something else. Yeah. And it's not even an empty orbital, right? That's filled. That orbital exists. There is some theoretical space that I can find. If I measure for an electron, I could find it. It's there. And so this is going to also stabilize this. But the really cool thing here, and how a chemist can control SN1 versus SN2, is that, okay, so I've talked about earlier how what is really, I want to make so many pictures. Okay, let's do a couple more pictures. So I'm going to bring this back for a second, and let's just realize how cool this is, or how cool it is to me, that this happens, and so this becomes less than X. The water is forming bonds. We are not just breaking the CX bond. We are making almost bonds with the solvent and the anion. So that's kind of the last point we got to. And in this case, I have changed it a little bit where it's now 4. 4 water molecules in a molecule. We know it's not 1. And we first put them so far away that they couldn't interact, and then we let them interact. We said, computer, I'm going to let these 4 water molecules connect. And what you were just realizing, what answer you gave me that is correct, is that this part of the O, this would stabilize the carbocation. And so we have to pause for a second and say, you might make the wrong assumption then that, let's say, instead of 4 water molecules, let's go back to just putting 1 into the computer. 1 water molecule and 1 thing. So let me go out of here. Wait, so question, does that extra proton just float around? Isn't that acidic? Which extra proton? Because all the protons are connected to water. They are just being drawn to the anion. So in the 1 molecule we ripped off, yeah, it is acidic. That is H is acidic, but it's not necessarily, or at least in the image we've been presented with, because the O latched into the carbocation. Okay, you're right. Interesting. But I want to, before we get there, we have to realize it's not possible for it to get there. And I want to convince you that this molecule was designed to go SN1 and not to go SN2. And so we can agree that or I want to get to a point where we can agree that when I bring in 4 water molecules and the molecule, which I haven't done a good job visually showing yet. Good, let's grab that. Okay, here we go. So we have here, and we have this. I need to edit it just a bit. So we know that before, so I want to kind of make another note in my, well, no, I can do it later. No, maybe I do it now. I don't know. Time for these. So where this discussion started, and eventually we'll get to E1. Where this conversation started is we looked at this graph and said all we did was break a bond. All we did was break the CX bond. So all I did was break a pencil. Ka-ching, took energy. All I did was break a bond. And so we know from intuition that to break a bond, it takes energy. So the thing only goes up in energy. And so that we decided to define this change in energy as, what is it, 219? I want to take this down just a second, because we're kind of doing a summary here, which might be helpful. Because nobody wants to watch a long video. Why would you? Okay, great. I would, but it has to be the right one. Okay, so pi, again, I just took a note of when we had this interesting conversation. And we defined that if all we do is break a bond, in this first example, we had one molecule. All we had is one molecule. All I did was break a bond, so all I did is go up in energy. And so we've been defining this as a variable because I don't know. It's x. And then we said that what happens next is, okay, if I take the molecule that I was looking at before, if I take this graph, or this graph, this energy calculation, and I add to it, now there's one water molecule in it. It is no longer one. Whatever this is, whatever this energy level is, they are so far away that they don't interact yet. I'm telling the computer it's so far away, but I know this energy cannot be one anymore. It is something else, which is fine. It doesn't really change anything, but it is one. And then we move to saying that, well, let's get rid of this one. This one isn't very helpful at the moment. It was cool what we talked about. But over here, then we came to this thing. So we said, okay, now let's not only let this leave, but choose that the water molecule is allowed to interact with it. And so the H becomes, I should just use the image because it's cleaner. All right, up at this new yellow bar, we now said that this X is, now I'm allowing the H, the partial positive on the H, to come near it. And so this is no longer X, no. And where's the nice little piece of thing I said? I'll just rewrite it again. Okay. So now I am not just breaking a bond. The light, or the blue dotted line, is a type of bond, a intermolecular force, an H bond. So I know it is not X anymore. I broke a bond, but I formed an H bond. And so X is now whatever this, or whatever we defined here as X just defines the energy to break the X away from the carbon, to break the bromine off, to bring this thing away from this thing. But now I form a bond with the hydrogen. Whatever this X is, it has to be less than X. So I've made the transition state, or I've made the rate determining step, I've made it smaller than it. And so if I add in more and more molecules, could you see as I add in more and more molecules, X gets smaller and smaller and smaller? Because as I add in on my 2D little chemistry world that I'm living in right now, right? We saw 4 water molecules are all stabilizing this. Now, there is a limit. I can only pack so many water molecules physically around bromine. So I can't say a million water molecules is better than 10. There is a physical limitation to how many water molecules can be around the bromine before the protons and electrons start pushing water away from itself. And that idea is going to explain my next point. So I'll just make that cute little note really quick that, okay, so I know it's not XMR, but I broke a bond, I formed a bond. Okay, so let's kind of take all of this and just kind of move it, or we can make our canvas a little bigger. Do I still have, no, of course I don't. Okay, and so let's just continue kind of having fun with this. So I'll go back here and I'll say this. And so we'll go back here and say, okay, now not just 1, but 4 water molecules. And so now as I let those come together, this becomes this. And now we can say that more than it being this, and I'm going to say, let's just for fun say, okay, it's less than X, we'll call it Y now. Now, Y. And so Y was 1 water molecule. Yeah, cool. So Y is 1 water molecule, but Y is, or whatever this is, this new value is now less than Y. 4 water molecules are now saying, great. But there is a physical limitation, so that's going to be the next graph. If we start to open our eyes a little bit and open our senses and start to question things, we'll say, but molecules don't react on a 2D plane. Can't you add in 2 more water molecules possibly and put them on either side of X? Yeah, I can. So now we have 6 water molecules. But wait, isn't bromine pretty big? If I look at its electron configuration, isn't it pretty freaking big? And isn't H pretty small? So maybe I can put like 12 around them, 20 around them, right? We could ask a calculator, or we could ask a computer, hey computer, how many water molecules can you stick around a bromine anion? What is the physical limitation? What is the lowest value I can get? So let me write this in there. So, okay, so I know bromine is big. I know that some amount of water molecules can surround it, but at some point, because I am physically limited, I can only have so many water molecules around the bromine. You can only have so many things around, or so many things around one person standing in a room. And so at some point, the energy I get back, so let's just say, now let's kind of keep going theoretical here and say, okay, not just 1, but let's put another cute variable in, but the Z amount of water molecules that it takes to get the maximum amount, or I guess it would be minimum, would probably be a better word, but for sake of this, I'll just say the maximum amount of energy I can save from my first picture, my X. How small can I make X? How small can I make as, because here in this example, we had no water molecules. How small can I make this if I allow a solvent to be considered in my calculations? And so, where did I put it? I thought I read somewhere. Where did I write it? Or maybe it went away. No, I'm just confused. Maybe it's elsewhere. It should be there. Oh, maybe when I went away, it forgot to write it. Okay. So let's just get rid of this. Okay, now not just 1, but as many Z water molecules as it takes to make x from the first graph the smallest jump in energy. And now I can finally go back to the point I was trying to make, because I think I've laid enough, conceptual, intuitive groundwork. So where a student might start to question me is they might say, okay, as you pointed out, with my whatever quote unquote assistance, if we can stabilize the bromine with the partial positive of water's OH bond, why does it not also go to the carbon? The answer is you need to look beyond the carbon cation. What is beyond the carbon cation? What is on the carbon that might stop or increase in energy the whole system to a point where the water only wants to stabilize the bromine? And that's the question I kind of want to just let you noodle on for a second. Sorry, I'm going all over the place. I'm just trying to make it a little bit better. And let me be more clear. Okay, now one water molecule, but I tell computer to move it not to the bromine, but to the carbon cation. And so this diagram is not yet 100% accurate because I need to pull in the thing that's missing, this thing. And we'll just call this, I'll name this in honor of you. This is the CAS variable of the pink arrow. Yeah, no, you will, because you cannot. What I have had to realize myself is that when I am forced to learn something new, like, for example, you teaching me these screenshotting things. Right now, if you ask me what were this combination, I don't think I would know because it's repetition. But what I want to kind of get you towards is don't look here. What could stop the water molecule from getting to the carbocation? Why is it that sterically hindered carbocations don't engage stabilization of their solvent? What would happen to this yellow line? It's blockage, and it's measurable blockage. As I bring these things near these things, what we're not being very clear about as teachers is that because I wanted to simplify things, I forgot that in simplifying things, I made things worse for my student. Because we know the carbocation is planar. We know that to some degree, this is probably a bad way to do it. Let's do it this way instead. Let's use technical writing stuff. Thank you, technical writing stuff. There we go. Okay, great. So we know, or I know, the C cation is a p orbital above and below the carbon. But why is it hard for OH for the part of the, why is it hard for the part of the OH bond, the O part that is partial negative, to interact with the OH? It's not even the carbons. It's the hydrogen. And that probably made no sense because I haven't drawn it yet. So again, boom, here is my C. Here is my other C. Here's my other C. And here's my other C. And I'm trying to explain to you, why is it that I can't have my O come from the top, and why can't I have it come from the bottom? Because when you look at a model and you have there are orbitals here of electron space and protons that also exert forces, that as I try to bring in my O minus, it is going to run into some issues of getting to where it needs to go, because it's going to bump into this and go off. And so to get a model kit out, I'm going to, yes, I know this is sp3 hybridized, just forgive me, but for sake of our discussion, I'll kind of force it not to be. Right, all I've done is I've taken my carbon in the center and I've put the 3 CH3s on it. All I'm saying is that if this is actually the p orbital and there's another p orbital up here, it's kind of difficult for water to come in and stabilize, because as all the directions it could come from, this doesn't work, gets stopped by methyl. This doesn't work because it gets stopped by hydrogen. This doesn't work because it gets stopped by hydrogen. So the one way it could is so infinitesimally small versus all the other ways it could approach this carbocation. Whereas on the other hand, in the earlier example, approaching the halogen is the most statistically likely thing that will happen. The halogen is just right there. And any direction water comes from, water will point its hydrogen at it and stabilize it. So this is what gets stabilized. Steric things that are big, like you said, it's too cluttered, it's blocked. This clutteriness destroys my probability of getting the O minus part to come into the carbocation. And so that's this whole unifying feature of, 237. We finally kind of made a point. And granted, it needs to be digested for a while for any of this to make valuable sense. Oh, where did I put that one? Not there. There it is. Can you go over here for me? Thank you. Okay. And so we basically finished that little thing at 237.38, and then we're going to walk into E1. So it's basically collision theory with probabilities. It's like, for the collision of water with this carbocation, it can get there and it can stabilize it, but only one or two water molecules might be able to stabilize it if they perfectly come from the top and perfectly come from the bottom of the carbocation's p orbital. Then we can stabilize it, but maybe only two water molecules. So the CAS variable of the pink arrow, fundamentally, I can still agree that it's going to be less than x. whatever this variable is, when I allow the computer to send the O towards the carbon, my orbital brain, what we're going to try to get you guys to start thinking about more, my orbital brain says to get to that p orbital, it's difficult, but it's very easy to get to these orbitals. And so what does water do in a sterically hindered system that's protic? It stabilizes the leaving group. It makes this less than y, and so that's why it stabilizes it. And it doesn't stabilize the carbon. Well, it does stabilize the carbon, but it doesn't stabilize it often. So the final point is that the point I am making is polar solvents easily and in great numbers stabilize the anion, making the slow step of breaking the CX bond lower energy. The polar solvent with a steric or cluttered or blockage or an R means like CH3s or ethanes or tetrabutyls. R3C connected to an X. The polar solvent with a steric or cluttered or blockage R3CX molecule can be but rarely, but in small numbers, because the carbons and CHs, or the carbons and hydrogens, block off the collision theory that would need to occur. No, sorry, Siri, not talking to you. And so this is why SN2 can actually happen in a polar solvent. If I take this molecule here and I say, nah, man, none of this. What if it was just a methyl itself? What if I remove the steric bulk? What if this was a primary carbon? Now, it's hard as hell to get the X to leave because of hyperconjugation and so many other things. And so SN2 happens where the anti-bonding CX bond orbital is accessible with collision theory. And if the carbocation appeared, the polar solvent would stabilize it and even further react with it. So I'm kind of going down a few rabbit holes here and how much I could talk about all these topics of, what the heck is hyperconjugation? Hyperconjugation is just that this is stabilized, this p orbital is stabilized because the CH bond electrons are donating their orbital space into that cation, stabilizing it, making it easier for the bromine to leave because what's left behind is stabilized. But if I remove the methyls, now I have no orbitals. All my orbitals are orthogonal to the p orbital, and so it's no longer stabilized. And so typically primary alkyl things don't. Their leaving group doesn't usually just leave. SN2 has to happen. A nucleophile, two things need to come together, not just one. So anyways, that's an important topic for probably another day or another time or in another life or in another timeline. But let's get back to the question that you kind of came in for, which is Can you explain what an E1 reaction is and how that relates to alkenes and easy stereoisomers? Yes, I can. So let's see if I can find a good image to screenshot into here. Not this, not this, not this, not this, not this. Not this. Close to this. Okay. Okay, so this is a great resource, so I'll put it in the chat a second. Or maybe I can't. I will email it to you. Okay, so this is, maybe we shouldn't do this one first. This is a good one. This answers your question, but we need first. We also need this one. Yep, great. And so let's reply to you as well and give you this one as well. So we'll look at the second email I sent you first, which just says that, okay, the mechanism is, because this is an E1 reaction, Windows Shift, I want to do S. Copies it to my clipboard, come over here, move over, and great. So it's E1. E1, so the slow step is unimolecular. The rate law has only one thing in it. The K is equal to, or sorry, the rate is equal to K times the concentration of the thing with the leaving group, here bromine molecule. And so the first step of the mechanism is that this bond is weak, and because I even have a polar solvent and I have negative things that can push on this bond a little bit, it could come off. And so once it comes off, there is a positive p orbital that is existing on this carbon. And rather than me bringing a nucleophile in and attacking it and doing a SN1 reaction, which is possible, which happens, right? What you should know is that this molecule, when chemists run this reaction, this molecule is also found. And Br minus is stabilized by water. So you can get three things out of this reaction. You can get this thing, and this thing. But if I'm just asking you to draw the mechanism that leads to the E1 products, you would draw these mechanisms here. And the way an E1 reaction works is that you don't attack the carbon like you did in an SN1 or SN2 reaction. Instead, you count one carbon away and look for a hydrogen bond. And so here we have so if this is my carbon 1, this is C1. If I look one away, there is C2A if I go to the right. And there's C2B, or I could consider this left. And both of these have hydrogens on them. Which one gets reacted with? Well, it's a steric question. It's probably likely that this one happens more often due to collision theory. It's easier for these hydrogens to be accessible. It's easy for things to come in this way via collision theory. Whereas it's a little bit harder to come in this way. But more substitute alkenes are more stable. And so this is the kinetic result. I gotta make sure I'm using this right. Right, this is the kinetic result. This is the thermodynamic result. In chemical reactions, the kinetic product forms faster, but the thermodynamic product is more stable. Kinetic products are favored under low temperatures and faster reaction times, while thermodynamic products are more likely at higher temperatures and longer reaction times. So again, I'm already going into maybe topics that are too much. The top one is the major one, right? It depends on your reaction conditions. What temperature am I running this reaction at? Am I allowing molecules to get here? Am I slamming them around? If I heat this thing up, I can get molecules to interact with something that seems difficult because I have to get past a whole lot of clutter. But over here, I can interact with this pretty easily. And so if I run this temperature super cold and the molecules are moving around so slowly, it's easier to attack number 2. It's easier to get the kinetic result, the fast result. The probability of collision theory is better here, whereas the probability for collision theory here is worse because the amount of space I can hit this molecule with has to be harder because there's freaking protons and electrons there. But the chemist can control these things. No. The chemist controlling these molecules. But that's what's so beautiful about these reactions is you can control these things. But anyways, so I think that answers your question at least. It does and it doesn't. You asked about easy isomer. So we explained the mechanism. We explained a little bit, went down a rabbit hole of there can be multiple products. There's a kinetic product and a thermodynamic product that goes back to orbitals and what's accessible by collision theory and running it cold, making molecules move around slowly so they can't get to the more stable product because they can't get to that orbital, but it's so much easier to get to the other orbitals on the left side of the molecule. It is so freaking easy. Like if I am running this reaction in like 1 degree above the coldest thing possible and I have infinite time available to me, I will more likely of a time be able to access this, and this might just be energetically inaccessible. I might have to like quantum tunnel to get to it to react here because my molecule is moving so slowly that the minute it feels the CH pushing it away, it goes away. It never reacts there. But if I heat this mother trucker up, I can react there. But anyways, let's now turn to this statement here is true. E1 eliminations generally lead to the more stable stereochemistry. So I'm not talking about thermodynamic and kinetic products here. I am, but not really. The E1 elimination generally leads to the more stable stereochemistry. And so if I have this molecule here that has this leaving group of bromine on it, on either side, I can make one of 2 products. Either this molecule is rotating around in space, and I need to have a better way to show this on a computer. I know it exists, I just haven't spent the time to figure it out yet. But I can get two products. So let's do what Cass taught me. Boom, boom, boom. Oops. Oh, I keep doing the wrong buttons. No. Great. Okay, so these are the same, but you can get two different isomers, right? You can get an E isomer and a Z isomer. And so if I think about the definition of these things, if I go into my ChemDraw, for example, and I just draw these two molecules out, and this is accessible to all Emory students. You can all get ChemDraw. It's part of the library's package that they bought for us to work with, because Emory is so dang fortunate. And one thing that a lot of students don't know about, and that I love, is I can go here and show stereochemistry. You see that? Object, show stereochemistry. So there is the Z product and there's the E product. But which one forms? Well, if we look at the mechanism, or we think about the orbitals, and we think about steric hindrance, and we think about electronics, here's the biggest goof of all time. If you're not sure on a test what the answer is when it comes to reasoning, just say sterics and electronics, because it's always one of those two. It's always that there's things blocking you, or it's that there's things affecting the electrons. It's such a goof that I always loved goofing on with one of my graduate friends, where it was like, it's always this, isn't it? And he really did not like that, because he was a very technically correct person. All right, so again, we have here, kaboom, give me that wedge, or at least it's not a great wedge, but it's something. And then this going back, and this going back. And boom. And so here, kaboom, this is, the first step is a bromine leaves. And so once the bromine leaves, let me write this in. Once the bromine leaves, the carbon does not have to be sp3. It does not have to support 4 bonds. It has to support 3. And so it adjusts to get those 3 bonds as far away from each other as possible. That means it goes sp3 to sp2. Oh boy, oh boy, oh boy, oh boy. No, these things can't be real. And so let's draw that. We have now yay, good. So now we have what my head sees is we got a big old p orbital here. Empty, theoretical, completely theoretical. And we need to align the electrons that are going to fill this. The HOMO that is going to fill this is what I'm going to highlight in red. I wish I could pull. Why can't I pull you out? There, okay, great. So these electrons here, sorry, I grabbed the phenol. You're just going to have to deal with it. Sorry. These red electrons here, there is a sigma bond there, a HOMO, a high occupied molecular orbital. When it aligns with this orbital and a base comes in, let's see if we can check the mechanism for a second. Oh, it's so ugly looking. Let's re-snip a second. Yes, got it. Kaboom. Okay. So again, the next step is that a base picks off a hydrogen. And so in my chem draw, what I'm trying to say is that this H is about to get picked off. The protons are going to go elsewhere. The electrons are going to stay. The proton of hydrogen is getting picked off by a base, just like acid-base chemistry. We're going to come and grab this hydrogen, but these electrons have to physically align in space with the LUMO they're going to fill. But this bond can rotate. So how does it rotate? It rotates in a way to get rid of steric hindrance. It's always steric hindrance. It's not always steric hindrance, but it's often steric hindrance. And so we can kind of run into this interesting thought for a second of this bond is rotating. This hydrogen that's going to get picked off. So let's kind of separate our thoughts for a second and let's expand this. I want a poster and I want it to be 20 inches by 20 inches. So let's kind of reorient ourselves a second. The first thing that happened that I did over here was, or maybe I should say over here. So let's just kind of go through it step by step in a second. And please, 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 everybody be aware, it's like, if you don't get it, that's okay. Some people have more experience than you. Some people have done this before you. It's okay if it doesn't make sense, and it's okay if it does make sense. We're all on a different journey through these things, but I just want to kind of remind us the first thing that happens, and let me make another timestamp that this is a good timestamp around this time. So we're at 3:00:55. E1 summary. Okay, so step 1, bromine just leaves. Step 1, bromine just leaves. So here, this thing, this bond stretches so far that at some point it goes and it takes its electrons with it, leaving behind a positive on my carbon. And if I go back into this text, now this becomes important. Once the bromine has left, once I've stretched that bond and it's taken the electrons with it and it's broken off, I'm left with a carbocation that's behind. And then I showed you over here that it's stabilizing itself. And now I need to get this orbital, or I should say these orbitals, all right, this is a bonding electron. The hydrogen is bonded to the carbon. And so these have to physically align in space for this reaction to occur, for me to make the double bond, for me to make the pi bond. Do you see the pi bond already that's going to start to form? It's crazy. It's crazy. As these orbitals interact with one another, as the H goes away, as the base. Okay, so step 2, Base takes only the proton, the hydrogen, and leaves the electrons, the HOMO. And so this goes away, base takes that away, and these orbitals will have to shift. They will have to readjust, or immediately, even rather than readjusting, they're going to start interacting with the LUMO. And so what they do is they make a pi bond. And so this becomes a p orbital that then interacts with this LUMO. And these two electrons, again, if I do like a quick diagram, right, these are the electrons left on the carbon once the proton H is picked off by a base. They are going to be the two electrons that go into the LUMO and make a pi bond. Because we already have a sigma bond. Like, you're not going to make another sigma bond. It's already there. So what's left to make is a pi bond. And so we can say that the what I'm trying to say here is that there are two electrons that are the electrons left on the carbon once the proton is picked off. And then over here is a pretty similar in energy level orbital. It is a cation. And so it's going to be a little bit more stabilized. And so now I have my LUMO, and it is empty. P orbital. Yeah. Well, the fact, okay, so here's the difficulty of assigning this energy level. It's a cation, so it goes down. But it's a p orbital, so it might go up. So I don't know where it is, and I won't expect you to know either. I expect a computer to know if I give it a basis set, but it's somewhere near enough to the other one that regardless, what's more interesting to the chemist is not where this is, but what's interesting to the chemist is that a pi bond forms, and a pi star bond can form but isn't filled. And so the two electrons go into the pi bond. Now the carbon and the carbon have a pi bond that appears, which the driving force is taking high energy electrons and bringing them down, while at the same time knowing I have created a new LUMO, a pi star up here. And so what I want to get back to the question that originally came into this office hour that has now taken me 2 hours to get to, but I love that it's taken me this long because this is the point. This is what I love doing, is talking about all these cool things, and figuring out how to explain them better every time, and develop videos that can do it for me, and how effective are those videos? How can I measure that? Anyways, that's more my lab research group at some point. Not today, though. Not enough for today. But not only can it be like this, but this bond, here's the sticking point. This red bond rotates, ladies and gentlemen. So if this bond can rotate, that's why you get two products. Is the phenyl ring, this is phenyl, is the phenyl ring on the same side as the phenyl ring when the orbitals combine to form a pi bond, or are they on opposite sides? Probably they're going to be on opposite sides because of steric hindrance. You're probably going to get the more stable result. You're probably not going to put two big mother truckers by each other. You're going to put them farther away from one another. The molecules go to a low energy state. So finally, let me walk down. What was my time I got to that? Oh, not bad. It's a 7-minute video. I think we can do faster. We can speed run that video later. Finish with E1 stereochemistry orbital check. Boom. Question answered. Still here in the office. Love that you guys are here watching me work, or maybe working alongside of me, or have questions on this, but I'm going to have this up, and eventually I'll hopefully have time. I'm so interested in finishing this quiz because I'm really enjoying making this quiz. Yeah. You may have, what you guys don't realize is, I know some professors have to limit questions because they do have other responsibilities. I don't. I'm just here for the summer to teach. Okay, constructing MO diagrams. That's a big thing. That's a big thing for me that I don't understand in 202. Yes, absolutely. And that is because first off, we're telling you an oversimplification with the purpose of hoping that you will understand the principles and methods and ways that when you realize we've oversimplified it, you'll at least be able to hopefully sit in some contentment of, I understand how the computer has made it a lot more difficult. But let me start easy with an easy thing. The simplest one. The one that we ask you to start on. The hydrogen MO diagram. And let me just see a second. Does EZ relate with major and minor? It doesn't. E and Z is just notation. So there's another crazy good resource. Let me see if I can make sure I find it. Or this is a really crazy important resource for chemists. So we all had to get together and agree what means what. And so I go to the IUPAC Gold book. And I'm going to search EZ. Oops. What do I want to say? How is it going to find it? Maybe that way? No. How about E-isomer? Let's do this more efficiently. What I'm trying to say is it's just rules. You just follow rules. And so what it is about is if you have your Z groups with the same priority on the same side, it's Z. If you have your CIP priorities that are different, the top two are on different sides, then it's E. So to me, it's kind of it's important that we decided language that we could use to communicate with each other. But for my students, as a teacher, I'm not sure how valuable I'm considering these things to be. It's just the CIP priority. It is a conventional order of things for it's important. It's really, really important. But is it what I want this class to be about? I don't know. Not necessarily, right? It's the same thing with RS chiral assign. We can go back to the Gold book and it'll super complicate things for us, but R&S just tells us that we look at the atomic weight of things to decide how we value groups. 1, 2, 3, and 4 is just that you look at the atomic weight, and that's how you decide 1, 2, 3, and 4. And so E and Z isomers are a similar type of nomenclature. And I love Z. The way I realized Z for myself was not that it's German, zusammen. I'm probably saying that horribly wrong. Zusammen, meaning together. I think Z means, they're sleeping on the same side. Z, 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 Z. The two highest groups are sleeping on the same side. And so, right, here it is. This is the Z isomer. They're sleeping on the same side. And the E isomer is just the other one. So here it is. Again, the E isomer is the things are on the opposite sides of the bed. The Z isomer is on the same side. They're sleeping on the same side of the alkene. So anyways, none of it matters. It does. It really does matter if you're going to talk to somebody. But for this class, for orbital theory, us getting lost in these systematic things when we can just go into ChemDraw and my students can realize over time that, we're going to say, okay, hey, ChemDraw, apply the IUPAC Gold rules. Apply the Golden Book rules that we decided a long time ago. Kaboom, E and Z. So cis and trans are E and Z. Be careful, not necessarily. There are differences between them. Right? If you say are E and Z the same as cis and trans, And so I like the EZ situation, whereas cis trans is a little bit more generic. So not the same, and I prefer, if I'm going to communicate with somebody, another expert, I prefer to use E and Z. But we can use cis and trans, and that actually is probably a better term in some ways. Why didn't we decide that we call Z cis and E trans? Now I'm getting into this whole question of, breaking the system. We shouldn't go down this road, right? I got other things to do besides talking about how can we change the language of chemistry to make education easier. That's a battle for a long time from now, that I am not particularly interested in fighting because I have the internet, because I have ChemDraw. Why would I fight it when it's like, it works. Technology works. So anyways, let's talk about constructing an orbital diagram just for a second, because that is real tricky. That's not quite, I got to get better at ChemDraw. Man, it is so crazy that I have not done ChemDraw in a while. No. Okay, can I do this? Yes, great. Okay, so you walked into this class saying that, all right, I can buy that hydrogen is H2. I believe it. But what is the MO diagram behind these things? Well, what it basically says is that, okay, in H, there are two wave functions. Let's think about the wave functions for a second. There are two I want to take this out of this and go back into Paint. So let's go totally into Paint and just say H connected to H, 1H, if I look up right, what is the electron configuration of H? Oh, it's 1s1. So I go in here and I say H is 1s1. So there is a poorly drawn, inaccurate s orbital that has one electron in it, and so there is some energy level that will just standardize here and say, okay, boom, that's where it is. And then on the other side of the MO diagram, we say not only is there the red H, but there is the green H. The green H. So that green H also has the same electron configuration. An electron configuration of this H is 1s1. And so there's one electron here as well. And then for a human being, this is actually easy. This is art. This is incredible art, where we can basically look at it and say, as I bring these two circles together, right, the metaphor I've been making in class, and I'm sure I'm not using that word right. Oh, what is a metaphor? What is a simile? I could look it up, but I have no interest in looking it up. I'll just draw a picture. So what we were talking about in class in some ways is, let's think about how we can have a little sand castle over here and a little sand castle over here. We have, and to make this a little bit clearer of an image, right, we have the red 1s orbital, and we have the green one over here. These are two sand castles on the beach. And as I let these two atoms bond, as I let them come close to each other, what happens when you push two piles of sand together? Well, after I push the two piles of sands together, it doesn't look like that. What would be a more accurate way to draw it would be to take my little, sand or whatever and say, it doesn't disappear. Yeah, it's a dune. Thank you. Yes, exactly. You have created now a little bit higher of a space in here. And so that's what is happening here in our MO diagram, is the hydrogen orbitals, their waves, right? If I think about musical theory, these waves overlap and they add to each other constructively, meaning that I no longer have two circles, but I have an oval. And now the hydrogen's orbitals have overlapped and made a new orbital. And that's where my two electrons live. And they're super happy here. They're like, yay, look at me. I have two parents and guardians. Rather than just having my one that I had before, my one hydrogen, because I was brought near another hydrogen, another proton on either side of me, I'm more stable. And so I literally wrote it to be at a more stable energy, right? There is, as you already know, this is all on an energy axis. I stabilized it because my sand castles built a dune. But what is the issue here? I had the computer take 2 orbitals. I had the human being take 2 orbitals, and I've only created 1 orbital. What must there be? 2 things go in. I have 2 inputs. What does my function say? If you put 2 inputs into a function, there should be 2 outputs. So what's the other output? When you pluck a guitar string, for my music people, when you pluck a guitar string, it doesn't just go up. And this is us walking into the quantum world for a second. Because you're right, you already answered it in the chat. You already answered it, but let's see. Sorry, I'm not going to pay for YouTube. You have to watch these ads with me. And you'll learn that I do buy, what is my deodorant? Do you want to take one guess at what deodorant I use? What do I buy? What does the AI, or sorry, what does it know about me? I know I should get ad blocked, but it's fun for me to see what do they know about me. Anyways, what do you see here? The guitar string does not just go up. What does it also do? It goes this way, and then it must go back the other way. The guitar string has both a, in this case, a positive X value, and then a negative X value. As the wave vibrates, it can go this way and then come back. And so with electrons, because we're in the quantum world, because electrons are waves, wavy baby guitar strings, what we start to realize is that not only can your wave go up, but your wave can go down. And so instead of us making a dune, what's happening is right, so this is the dune. We'll keep this one. Chasing thunder. Right, so that's the Dune analogy as to how we got the lower one. I love Dune. What a great book. What a great movie. All right, so what's the other analogy here? Not only can the wave function go up, but it can go down. And so we show that to chemists. If I go back to my ChemDraw, we show this by saying it's not just this. This is not the end of the s orbital. This is guitar string going up. This is guitar string going down. Would be, we typically just do the other color. And so rather than it being shaded in, right, look at a p orbital for a second and remind yourself that what I'm saying is true. Right, in a p orbital, you have a shaded section and an unshaded section. So the guitar string can go up and the guitar string can go down. So to bring it back to the sand analogy, the computer says you can add, you can have your dune, so your red one again, so I'm just saying this one here is this, and it is the filled in orbital, but the green one, this one, oops, what about this one? It doesn't have to be filled in. It doesn't have to be a guitar string going up. It can be a guitar string going down. And waves add up constructively and deconstructively. And so now there's not a dune anymore, but what is there instead? A hole in the sand, or a hole I've dug into the beach. And so now what do you think is going to come up as I bring my sand castle over to my hole? As those overlap, the result is I have some of my hole left over here, and I have some, and I have some of my, right, I can't completely move the hole over because protons stop me. If I move these all the way together, the wave would collapse. The sandcastle would fall into the sandcastle shaped hole. It would form nothing, deconstruct. But that doesn't happen. We cannot stack protons and other protons. Well, we can, but here we can't. We're not doing nuclear chemistry. We're only bringing them close enough together before we're forced to push them apart. And so as we push them together, there comes a point where it stops. And so some of the hole is not filled by some of the sand, and some of the sand has not fallen into the hole. And so we see now that I was fixing my bad drawing. So we have some hole left over in the sand, and we have some amount of sandcastle that's been built up. And so to transfer this back, there is another orbital that exists where instead of there being electron density between the two H's, and I should be more accurate, there's a little bit of a blump over here, Now my blump is mostly on the outside. And there's very little glue holding these things together. So let's see somebody who actually did this and posted it online and has a better picture of it that I agree with. Ugh, ugly pictures. Ha! Ha ha! Beautiful picture. Oops, I'm not ready yet. Now I am. So what if a computer does it? Because Cam can't draw to save his life, especially with a pencil. He's telling you that they look like that thing here and that thing here. What do they actually look like? When a computer does it, looks like that. The glue, the dune. The sand here has fallen in and started to deconstruct. And so now there's a hole, there's a way to break this bond. So that is so it's lopsided because that electron position imbalance. Well, it's actually not lopsided because they're the same atom. But when we get to the CO diagram, so let's look at the CO diagram, or maybe the carbon monoxide MO diagram. Let's go up a level a second. It is because of electronegativity. Yes, exactly. Yes, it is. 100% it is. And so baby, I'm not a rose, I'm a wildflower. And so first at its simplest, let's just look at it at its simplest. Okay, so let's go up a level. What is, if I pull out an internet browser, first, we're going to consider only the orbitals of the highest shell, which in this case is 2. Because if I look up carbon electron configuration, 2s2, 2p2, with helium being 1s2. So on this diagram, the 2s2 electrons have been shown to be at a certain energy, and the 2p2 electrons have been shown to be at a certain energy. We're also, though, bonding this now with the more electronegative, so now things are going to get lopsided, the more electronegative oxygen. This is 1s2, 2s2, 2p4. So we have 2s2 and we have 2p4. How do these overlap to make the CO bond that we see? Well, we know that the 2s orbitals can overlap both constructively and now deconstructively to form, so there's no energy help here. It's like, yeah, I'm gaining some energy, but I'm also losing some energy. So, this was not very helpful. I could have stayed apart. I didn't have to form this bond because I had to fill both the bonding and the anti-bonding. But up here, things get more interesting because of the p orbitals, what is it? It's px. Okay, well, they're defining it as pz, but I would define it as px to a student because I'm seeing it in my head as a graph on here being it. So let me edit it really quick. Get out of here. Because I'm allowed to make decisions too. Boom. Px and pz. And so hopefully this helps a little bit where if I say it's like, okay, great, I can go back to even, and it's not very accurate, but trying to find out, I just said I'm having to draw the orbitals myself. Can I take it from somebody else and never give them credit? Just kidding. Nice. Beautiful work, whoever did this. Okay. Boom. Oh, I keep doing the wrong thing. Boom. All right. So, oh my gosh, so the calculations are different. Fun. We'll just agree with them for now. Depending on what basis set they used. So here, 2s forms the dune that we talked about. The sand aligns. It's two sand castles or two holes. It's two waves that construct, or it's two waves that deconstruct. And there also, though, is a deconstructive orbital as well. And so that's the molecular orbitals. That's what this diagram is missing, is that picture there. And what this one is missing is that picture there. And again, I'm not hyper concerned with us knowing exactly what orbital is where without calculating it, but I am willing to talk about what are some factors that change your energy level. Hybridization, electronegativity, overlap. Like we talked about that things in my class PowerPoint slide already about orbitals that are sigma bonding versus pi bonding versus lone pairs versus anti-bonding pi bonds versus anti-bonding sigma bonds. We do have ways to at least talk about where they should be, but until we calculate it and use different basis sets, things change. But maybe I can kind of combine these two together because I kind of want to stay in the simple world for now because we might be wrong, but it'll help me make this a little bit easier to explain. So this is this orbital here. This is this orbital here. And now there is the px orbital. What is the px orbital? Let's make sure we draw this. Px is along the x-axis. Py is along the y-axis. And pz is going into my computer screen, so I could tap the back of my computer screen, and that's where that orbital would be. Or I can be grabbing in front of my computer screen, and that's where it would be. And so, because we're bringing these bonds together on the x-coordinate system, the x electrons that are in the p orbitals would overlap. Bond on bond, the electrons would be in between the atoms, and so that would be this more stable sigma bonding orbital. It makes sense that this is lower in energy than what's about to come next because the overlap is better. The next thing that would happen is these are my pz orbitals. They're going out of the screen and into the screen, and so that represents my left blue electrons that are up top, and then my py orbitals that are up and down on my screen are over here. And so these make pi bonds, these make sigma bonds, these make sigma bonds in anti-bonding. And so we know that this molecule bonds because we have more bonding electrons filled. We have not added too many electrons that we've made anti-bonding orbitals, which look like they've only drawn... Ooh, wait, I messed up. This is I messed up because the shading on this they did on purpose. That's the shading where it's a sand castle and a sand hole. Sand castle and sand hole. And so they don't have a picture. That would be, I guess. Oh, they did. They did. I'm sorry. Let me... You did it right. Let me snip it for us and bring it back in. Right? I didn't realize until just now. No! I didn't realize until just now that they had done it perfectly all along. Let's go up here. Go over, go over, go over. That's the Z. That's the PY. I gotta get a little bit closer on it. Kaboom. And so that is me explaining MO diagrams where don't worry. I really don't want you to worry about what is right. Let the basis set and the computer decide what is right. Focus for you on how can you argue for which one. If the computer says one and the other computer says the other, what does each computer value that puts these orbitals at different levels from one another? The sigma star is so much more destabilized that it has to be higher in energy than things that are bonding. Okay, that would be a reason why this should be here, like it's in the other person's diagram. Or we can say, but because they're smaller orbitals, because they're 2s orbitals, they're a little bit more stabilized, so they must be lower in energy. So focus less on what's exactly right and focus more on what are some universal truths about it going sigma, pi, lone pair, anti-pi, or sorry, pi star, sigma star. That's reality. That we can argue about all day very clearly. But these little intricacies we can focus on a little bit, but I'm going to be careful not to be an ass about it and remind myself that these are all just basis set calculator results. So anyways, keep giving me questions, but now I can even write another video I can clip. Oh, I'm teaching and I can come back because I recorded it. Yay me. Well, I didn't actually record it, but it's there. I can tell them what things to look for. Good. Do grocery shopping. See you in class on Tuesday. See you in class. And I am going to continue to just kind of step back out of this stuff. And we'll likely come back to it as other students. Oh, I'm definitely going to check out your stream. In fact, let me set a timer for that. Because I think you said it was 11. Baby, I'm not a rose, I'm a wildflower. Check the chat. I think you said 11. And I'm coming up to playing my Dota game today, which I'm very much so looking forward to. 11, great. All right, back to making the quiz. Oh no, I have a German. I wonder how it's pronounced. Am I saying it right? Zusim? Baby, I'm not a rose, I'm a wildflower. Okay. Zusamin. The song by Rammstein? What's the song by Rammstein? The German song by Rammstein. I do think I've heard of Rammstein before. Zoo-woman. Zoo-woman. Domen. Zudo-woman. Domen-woman. Zudomen. Zudomen. Zusamin. Zoo-woman. Darn, autocorrect? No! No! My German tutor! Summon. Let me look at it again. Zusammen. 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 Some in? Yeah, zusammen. Or some in. Some in. Some in. My German tutor is trying to help me know German because chemistry started in Germany. So why is there a lot of German in chemistry? Why was angewandte, or I'm sure I'm saying that wrong too. I can't wait to have my German tutor tell me how to pronounce one of the greatest chemistry journals of all time, the OG ones. But anyways, okay, enough German. I can't do more German right now. I want to learn German at some point in my life, a little bit, but I need to get back to writing this quiz, this bite-sized Duolingo brilliant quiz. I need these things for sure, though. Okay, this is from Wolfram Alpha, so let's make sure we credit them so we don't get sued. No. I didn't do it right. But that is part of the whole frickin' process. All right, I think we got one for 4A. Let's add an image, browse. Okay, and I linked in the question. So, we're good, Wolfram. You don't have to come after me. Not yet, at least. Make sure I can see my chat again, just in case something else comes up, or somebody comes in and has a question. Instead of just working alongside of me, it's fine to work alongside of me. We're in it together. I'm learning, you're learning. All right, in honor of what just happened, I'll listen to one Rammstein song. I can't stream it, obviously, or this will get copyright struck, and it won't be Creative Commons anymore. That's the only brutal thing, is I do have some music coming my way that I can use without copyrights, but how will the class window work for the exam? Great question. Over this weekend, it's on my to-do list. After I get this quiz done, the next thing I'm going to do is do a midterm vote on Canvas. And so I'll probably talk about it hopefully at the end. I mean, hopefully this quiz gets done. Whenever this quiz gets done, or I decide that it's good enough, I'll post it, and along with it, I'll say, by the way, you also need to fill out this form about when you think you can take the quiz on Wednesday. Because I don't want to use a lecture time. Even though I could proctor it in real time, I don't want to use a lecture time to watch you take an exam. So instead, you're going to take it on Wednesday. I'm going to look at proctoring resources, but we need to decide as a class what window works for everybody. And if it doesn't work for you, why doesn't it work for you? And provide proof of why it doesn't work for you within privacy FERPA policies. But I need to find a time, and you're going to rank them. It's not that you choose only one time. It's that you rank a couple of choices of, this is the time I absolutely cannot do, these are the times I can do, and this is the order I prefer them in. Then we count them all up that everybody can do, and we say we take out the lowest one, redistribute those votes to their second choice, do it again, until we get something that everybody, democracy, decides this is when the exam is. That's when it'll be. That's when you'll have 3 hours to do it, or whatever my accommodation is, 2 times the hours to do it in. And that's when you'll do the exam. The first thing, though, I have to ask is, when can't they do the exam? Because if one student can't do the exam at a certain time, first I need to know why, and they need to prove it to me. And then we'll go from there. But that's how the class window will work. You're going to get 2 times, or sorry, not 2 times. Whatever the accommodation is, my highest accommodation, that's how much time you'll get. The quiz or the test should be an hour and a half. that a reasonable student could do, not me, a reasonable student could do in an hour and a half. Then I take my biggest accommodation, whether it's one and a quarter, one and a half, one and seven, three fourths, two times, and I do. That's the window that you'll take it in, and so yeah, that's coming, but it is the second thing on my to-do list. It's less important to me because I need this quiz to get to you guys so you're ready for the exam. We can worry about the exam over Saturday, Sunday, and Memorial Day. We're not even doing anything on Monday. So we have time to be ready for the exam on Wednesday. This quiz needs to be made and made well in a way that I like it, in a way that I'd want to be taught. So that way you're actually ready when the exam comes, because the exam, because it's open book, because it's open note, because it's open resource, because I'm worried you're going to just ask the chatbot to answer things for you, I have to design it in a very particular way. And that will take a lot of time as well. But so this quiz will be a study guide. Yeah, I would say that this quiz will hopefully be a foundational study guide. Do you understand foundationally what's happening here so you can go explore elsewhere? Your foundations are strong. Can you learn from other resources that I hope to provide you? I hope other students provide you. I hope I crowdsource teaching in some ways. Yes, I need to be one of the most important parts of the crowdsourcing of teaching and studying and what is a good resource. But I know there are other students out there who are going to get 100 on my exam because they know something that my other students don't. They know resources my other students don't. And I really would like to get them to give it to us. So anyways, I got to use the bathroom really quick. So I am going to be back very, very shortly. Okay. Little bathroom break for me and my dog. All right, let's worry about day 7 lecture later. Okay, back to talking with a chatbot. Don't need that anymore. Don't need that anymore. Don't need that anymore. Don't need that anymore. Could use that. Don't need that anymore. Okay. So what was I? I was thinking about something here. Oops, I don't want to do that. So in here, let's save this answer, and then to this add an image. Out of the 5 out of class participation, no, you may have as many questions as you want. No need to apologize. That's why I'm here. I know we have to do the project for this class. Can we have the same project for the rec letter, or is it something different? Also, can each of these questions count as 1? So what you're doing right now is out of class interactions. And so every time you asked me a question, that would be like, yeah, that was a participation. So asking me about the exam window, 1 participation at today on this live stream. And then asking about this project, another 1 question, completely legitimate. And the issue, or what I will say is the group project. I need to talk about the group project. That's something I got to add to my list too. But we need to get through the content that it could be on, which is coming soon. So we have some time on that, but let's add it to the list. Let's combine these a second. Or let's just add it to, where should it happen? Before I do week 2. But the group project is a part of the recommendation letter a little bit, but I don't think it's as much a part of the recommendation letter because it's a group project where it's a little unclear to me. It's hard for me to be specific about what you did, whereas the lab project, I could be very specific about what part of the paper did you write, or what multiple parts of the paper did you write or contribute to, I guess would be a better way to say it. Let's unlock this and make it a little bit smaller. Yay! And lock it again. So, yes, this absolutely counts. Both questions count. Both times you interact with me count. And the group project will start once we're done. Let me make sure I've actually made that what it says on Canvas. So let's check a second. The first week of Chem 203, which we are coming to the end of. Well, no, it is today. Today would be yesterday was the end. So we have finished it. So we can talk about it now. Because it was this day, this day, this day, this day, and this day. I'm asking for you to create content on, or 202 to 203. So it would be a great day for me to talk about this group project now. Complete set of content that provides support for learning objectives for a day in the first week. And I need to provide, well, no, they should all have access to this. To get in this course, not everybody, unless if you got credit, but most people will have access to these learning objectives for some course they've been through. So great. And then I get it. Yay. I get to hold on to it. Yay. Ha 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 ha. Not only am I making you teach other people, which is important because if you can teach it, you understand it, which will be great. And I can use it to teach other people because if students develop it, it's probably better for students than if when I'm developing this quiz is good for, or over here, this quiz is good for me. Is it good for my students? I'm curious if it is, and I want to see if I can measure if it is. How do I measure it? That's assessment. More pedagogy that I'm not ready for yet. So I'm just going to first make what I want and realize that that's enough. So, anyways. But thank you for reminding me of another thing I need to do. Okay, Rammstein. Here we go. Listening to some Rammstein out of respect for, what was it again? Together in German. I can even probably hear it a second. I think it'll come on stream a little bit. Yeah, let's turn on my desktop audio and listen a second. All right, so in honor of Rammstein and Z Isomer or
Zusammen.
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 Something like that. Listen to some Rammstein. You know, it's actually a good song, though. I shouldn't say that. This is a good song. What is it called? The bass or something? Yes. I can't play it, but because this will get struck. But great freaking song. Thank you, Anonymous. I love that I have no understanding of who you are. You could be my mother. You could be my grandmother. You could be Professor Kint. You could be Professor McGill. Or you could just be one of my students. Because you're asking these questions, you're likely one of my students. But come back anytime. The door is mostly open. Oops, I have an email open somewhere. Hmm. go back a little bit, get more vision. There we go. So think about what you're doing. What is the... No! Alright, we gotta snip a picture out of this. We're trying to get somebody to give us access to music. Okay. And then I haven't washed that shirt, so I gotta wash it. Alright, come on. I know you're gonna show up soon. Okay, let's edit this. Let's refine it. All right, let's take a break. We're gonna go do some. We're gonna do our Dota game. So, I'll be back for later stuff. At some point, I'll be back.